So I'll just refresh again. I'll go back to yesterday's portion once again. Now, if you see this, yeah, it looks very complicated, but as far as design is concerned, I'll take you back to that diagram. One more diagram is there. See this one. So this gives a little bit a simple way of understanding this one. Now, if you see this diagram here, you will understand how it works actually. So you can see these two are, see one is this one more is this one. There are two gantry girders like this. They are running in this way. And whatever truss you are seeing, it is crane girder. And you can see there are two wheels for the even for the crane girder. Actually, these are the two wheels through which the reaction from the crane girder is transferred to the gantry girder. So this is a more simple way of understanding, because if you see this diagram, that is it looks very complicated, but actually when you go to the industry there to see these gantry girders, because as you know here every industry will be having so many gantry girders here. Okay, now this looks a little bit this one, unless you go and see this physically, you go and see this one. But as far as design is concerned, you can depend on this diagram and try to understand what is what here. So you can see this one. Whatever rail and all I was telling, you can see the profile. The profile of gantry girder is one channel and one eye section. All are available in the steel tables. We don't have to manufacture this, just like plate girders. Plate girder means those sizes are not available in the steel table. Actually, specially we have to manufacture them. Now you can see the rail, whatever I was telling, weight of the rail is 0.3. Okay, 0.3 kilonewton per meter and all I was discussing this one. That is nothing but this one. This is the rail on which see all of you mute your this one. See on which you can see the weight of the rail is also taken, and you can see those point loads, whatever I was telling, the reaction is converted into 2 point loads. RA is equal to RA by 2, RA by 2, through which through these two wheels those 2 point loads are transferred. We have to check, see we have to check for what position of these two wheels, because it is moving in this direction. Okay, as you can see this diagram here, you can observe this one. You can see this diagram here. Now this crane girder is moving. You can see this how it moves in this direction as well as in this direction. Okay, and crab, that is this one moves like this or like this also. It can move in either direction like this. So now our what I did was, at what position of the crane girder we got maximum bending moment. That was by influence line diagram only we are able to find that one. That whatever I have given, that is for every problem, that is same, that concept is same. And for what position of these two wheels, where I should place these two wheels of crane girder so that I can get maximum shear force. So it is very simple. If you see, if you have studied influence line diagrams, directly one of the loads, one of the wheels should be directly resting on the end of the gantry girder, starting point of the gantry girder. Then only I'll get maximum shear force. And at some other position that I discussed yesterday, at some other position of these 2 point loads, I am getting maximum bending moment. It means since this crane girder is moving continuously, that side and this side, we have to identify a critical location where the bending moment is maximum. For that bending moment only, I have to design the gantry girder. Again, you have to locate the critical position where shear force is maximum. Because these loads are not stationary, the crane girder is moving to and fro here. Let us go back to the previous yesterday's class here. Observe this one here. I'll just go through this previous yesterday's class. In 10 minutes, I'll try to cover this one. You can observe this here. See, this was the problem. Once again, I'll go through this. Design a gantry girder simply supported to carry a hand operated. I already told you sometimes it is power operated, sometimes it is hand operated. I'll give you that problem also. Minor changes will be there. Traveling crane for the following data. Span of gantry girder is 6 meters. Span of crane girder is 15 meter. Crane capacity is 200 kN. It can lift a maximum of 200 kilonewton. Self weight of the crane girder is 200 kN. It is for the entire length. Total crane girder weight is 200 kN. Per meter it is 200 by 15 because 15 is the span of crane girder. Self weight of trolley is given. Then maximum hook approach is given as 1 meter. Distance between the wheels is 3.5 meter. Okay. Self weight of rails is, as I told you, 0.3 kN per meter. Now what I have done here is, see this one. Step number 1 was determine the vertical forces. Self weight of the crane girder is 200. Weight per meter is 200 by 15, 13.3. Weight of the trolley or crab, see this, is 30 kN. Crane capacity is 200 kN. So the crane load, observe here, the load that is the crane is supposed to carry is weight of the trolley plus how much weight it can lift, that is 230. In this problem both are same, don't get confused here. Now when I say crane capacities, it can lift a weight of 200 kN plus trolley weight. So the crane girder is capable of carrying this much of force, that is 230 kN. Hook approach is 1 meter. So what I will do here is I'll start this position. I'll keep hook approach here. See total load that is acting on the crane girder. See first I have to deal with crane girder, not the gantry girder here. Step number 1 is related to crane girder. So crane girder span is shown here, 15 meter. A and B are the supports. Whatever hook approach is given, that much is taken 1 meter here for 230 kN. Okay, it cannot cross this distance. Okay, the box will touch the wall actually. So 1 meter is hook approach is given, 230 is calculated here. Okay, then this UDL is 200 by 15. UDL is, that is dead load of the crane girder. Per meter is 13.3. Total is 200. So sigma MB is calculated. Somebody has yesterday corrected it. That is it should be 1.4. Okay, it is 1.4, but the final answer is 314 only. 4 I forgot to write here. 4 should be written here. I'll correct and I'll send it. Sigma V is equal to 0. RB, all this RA and RB are calculated. This reaction is transferred to gantry girder through 2 wheels of trolley. Actually, this is I'll just correct it. There is there may be later there will be confusion here. What I will do here is two wheels of the crane girder actually. Maximum wheel load on the gantry girder, that is RA, is distributed on 2 wheels, that is reaction by 2, that is 157.35, that is again factored, it is factored to 236.02. Those are the loads. Okay, then first this is, as you have seen here, it is related to crane girder. Next we will start the gantry girder because I need these values. I need the 2 point loads on gantry girder. So step 2 is related to gantry girder now. Now what I have done is there are 2 point loads. Imagine these are the two wheels of the crane girder resting on the gantry girder like this. So vertical bending moment consists of bending moment due to live loads, due to impact load, bending moment due to dead loads. So this is how it is calculated. This all approximation is there. Now observe, maximum bending moment under second point load occurs. Under second point load occurs here when centroid of loads and midpoint of span are equidistant from the second point load. I already told you this method. Mark center point here, then divide this distance by 4 and place the first load at that distance. I already told you this placement. If you are good in this one, influence line diagrams, if you are not good in that, you have to remember what I am telling right now. Okay. So mark this one midpoint. Let us say this is the midpoint 3-meter line, 3-meter point here. Now you are having a distance between wheels as 3.5 meter. Okay, these are the 2 point loads which are to be placed anywhere on this span. So distance between them is 3.5 meter. Now what I will do, I'll divide this by 4, which is 0.875. So I'll place first load. You can see this like this. This is 0.875. So like this you place the first load. These two I cannot change anything here. Distance between wheels cannot be changed. It is 3.5 remains as it is. Now I have taken the midpoint here. From midpoint I am going to divide this one by 4. So that much distance will be kept here. So you can start like this. You can start like this. Place this one here. Then what you should do, the next load should be kept here. Next load should be kept here, that is second wheel load. How to place this one is total is 3.75 minus this 0.875, that much is the remaining distance. Like this you can also place it. Only thing is that you should be able to get when you calculate the reactions, you should know what is this distance in order to find reactions. Observe this figure. Only when you know this distance, then only we can get all the reactions or whatever, because moments are to be calculated now. So once you place these 2 point loads in such a way that I am getting maximum bending moment under second point load, I'll show you that one. Diagram is there. So with this much information, you should be able to find this distance. How much is this distance? Distance between the trailing, that is trailing and leading point loads are there. So this one is green is trailing, red is leading point load. So distance between the support and the trailing point load should be calculated. It is not a, I told you it is very simple now. Divide, you place first load here, leading point load here at a distance of 3.5 by 4 from the midpoint. You place it like that, get the remaining distance, get this distance also. In this way, you have to place it. So centroid of the loads you got it. Finally, you are able to find out this is a C and D. Remember, these supports are named as C and D. These are named as C and D. This is C, this is D. The reason is already AB is used for crane girder. Now you can see. Now that is I'm able to find out maximum bending moment due to live load is calculated now 355.25. Okay. Remember here these it don't multiply 1.5 again here because already I have multiplied point loads only. 236.02 here you can see, and 236.02, these are already factored loads. Whatever bending moment you are getting, it will be factored bending moment only. No need to multiply again with 1.5. So finally we got a maximum bending moment as RD into 2.125. So 355.25. Is it clear this one? Any questions here? Any doubts are there for binding? What I'm doing is, see how to understand this one is, you place these loads and it becomes a strength of material problem. Find the reactions, find the moment, that's all. Okay. You just place these 2 points loads in using ILD, influence line diagram, place it like this. Now it is a strength of material problem having 2 point loads. Simply supported beam with 2 point loads. In that way you find out the maximum bending moment. So it is at 355.25. Now 20% of this will be impact load because it is continuously moving. There will be impact because of continuous movement of the crane girder as well as crab or trolley. So you can see this final formula here. Vertical bending moment is equal to bending moment due to live load is calculated. 20% of that is again added. Then bending moment due to dead load is calculated. Is it clear this one? Dead load. So dead load, when you want to calculate the bending moment due to dead load of gantry girder, you assume some weight as 2 kN per meter. You start with this assumption 2 kN per meter. Usually 2 kN per meter is more than sufficient. So you have to assume this one here to find out bending moment due to dead load. Then here I have to multiply 2.5 to get factored dead load. Okay. Now you observe here, assume dead load of gantry girders to total dead load. Dead load of gantry girder plus weight of the rails which was given in the problem as 0.3. Weight of the rails. I have already shown you that figure. Okay. You can see this green colored whatever I am doing here. This entire thing is a rail. Okay. So weight of the rail is given like that. Okay. So this is a finally observe here 2 kN per meter dead load assumed. Okay. 0.3. It is 2.3. It is factored again 1.5 into 2.3. I am going to factor the dead load of the gantry girder, dead load of the rail 2.3 factored 1.5, 3.45. So directly it is W L square by 8. W into L square by 8 is the third component. Now you can look at this main formula here. Bending moment due to live load is calculated by placing these 2 point loads at suitable positions. Bending moment due to impact load is 20% of this first term. This is WL square by 8, where W is the factor dead load of gantry girder and rail. So in this way, I have calculated the vertical bending moment. It is in the next page. It is in the next page. You can see here. You observe this one. So maximum factored moment due to dead load is WL square by 8, which is 3.45. It is a factored load of gantry girder and rail. So span is 6. Span of gantry girder is 6. So the value is given as 15.52. So add all the three. 355.25, 20% of 355.25 and 15.52. So 441.82 is the factored vertical bending moment. MZV. MZV means V for vertical moment. Now vertical shear force. There will be horizontal forces. That is why we have to write like this. Horizontal shear force will be there. Horizontal bending moment will be there. The member is subjected to horizontal forces also, not only vertical. So let us see that. Let us start the step number 3. Position of loads to get maximum vertical shear force is shown below. Directly place over this left support. These 2 point loads, wheel loads are there. Okay. You just place them like this. Again, this is the dead load as usual, 3.45. dead load here. This dead load 3.45, as I told you, it includes both rail as well as gantry girder. Now you place it like this, then find out the reactions. Now R dash C, R dash D. Why it is R dash now? Because CD reactions are calculated for another position of these 2 point loads for maximum bending moment. Those are RC and RD. Manoja, you erase it.
Sir, by mistake it came.
Now observe here. That is see previous page I will go. Why it is R dash C, R dash D, to know that I'll go to this. See this. For this position of point loads, RC and RD are calculated. For this position of point loads, again reactions are calculated. The reactions will be different because point loads are shifted now. That is why R dash D, R dash C are given. Sigma dash D. Bending moment means sigma dash D means you have to use algebraic sum of moments about D is equal to 0. Find out the reactions R dash and see, it is simply only the notations are different. Again, one more problem of strength of materials wherein 2 point loads are there and UDL is acting on that. Like this, you find out the maximum vertical shear, and here we are going to concentrate on shear because bending moment will not be as much as 441.82 for this position. For this position of point loads, bending moment will not be equal to 441.8. My interest is only shear force here. That is why shear force is calculated. Now observe this. Maximum vertical shear force due to wheel loads is 334.36. In this way, you find out the shear force. So maximum SF due to impact load. There is an impact because weight is suddenly lifted, it is carried to some other place, again it is dropped. There is a lot of horizontal movement is there for this gantry girder. Gantry girder is subjected to loads which are not stationary, which are moving horizontally on it constantly, continuously. That is why something called as impact has to be considered. So impact calculation is very complicated actually, but in your syllabus or in the for this particular semester, 7th semester, simply 20% of 334 is taken. It's a very debatable and it's a very this one 20%. How you arrived at 20%? It is after experience and after so many equations. Finally, they say just use 20% of this as impact. Okay, so there is an impact has to be considered, which is vertical again. 20 by 100 into 334, 66. You add this one. So maximum vertical shear force due to self weight must be calculated. Now observe here. What I have done is just observe this. How many are there now? One is this. One is this one. One more is this 20% of 334.36. One more is 10.35. Because there is a vertical shear force due to self weight will be there, WL by 2, 3.45 into 6 by 2. You just add these three, you will get the maximum vertical shear force, which is there in the next page. Okay, see this. VU superscript is V. These are vertical forces related shear force, 411.58. Now let us go to the lateral forces. You can see this diagram here. What is happening, you'll understand. See this. Span is again 6 meter. Forces are acting in the horizontal direction on this beam, on this gantry girder. Which are those horizontal forces and all? You will see that one. Now what I have done is again CD is the, every time I am using CD, but while calculating reactions, I am going to use RC superscript H, RD superscript H, because these reactions are related to horizontal forces. That is why superscript is H. Okay, so you can see that the span is used 3 times. Gantry girder span is used 3 times. One for maximum bending moment for a specific location of point loads. One more for maximum shear force. Again, the positions of point loads were shifted. Third case is again I am calculating the reactions with respect to horizontal impact forces, lateral forces. You observe this one. Lateral forces. Lateral force is developed due to the application of brakes or sudden acceleration of trolley. Whenever we apply a sudden brake to the trolley, okay, so or suddenly it is accelerated, okay, there will be lateral forces produced. How to calculate this one? Observe here. How I am getting 8.625 and all that. Now observe this. See, right now, don't think too much about this. It is there is a separate book is there. You need to separate book is there for this. How to find out lateral horizontal forces. But in your IS code has simplified all this. They have simplified this one. See, a lot of complicated equations are there to find out the equivalent horizontal forces acting whenever sudden brakes are applied to the trolley or suddenly it is accelerated. Okay. Now, lateral force on the rails is, see, 10% of, observe this one, how it is calculated. It's very important calculation, very simplified by the code book. You can see this 10% of crane capacity trolley weight. So the crane is capable of lifting 200 kN, okay, and weight of the trolley or the crab itself is 30 kN. You add these to 10% of that, 23. 23, 10% of 230. This load is distributed over 4 wheels. Now, these are 4 wheels, these are related to the trolley now. Those wheels were related to the, those 2 wheels were related to the crane girder wheels. Now, I am looking at 4 wheels of the trolley. So that is why horizontal force on each of the wheel. There are 4 wheels for the trolley. Each wheel is subjected to horizontal force of 23 by 4, which is 5.75 kilonewton. Again, you factor it. It is 8.625. So you can see this 8.625, 8.625. Again, the distance between these two is also 3.5 meter. Are you getting this point? So 8.625 kilonewton. To get maximum horizontal bending moment, loads must be placed in the same way as placed for maximum vertical bending moment. See the figure 2 and figure 4. What it means here is, what it means in this case is, just read this one. To get maximum horizontal, see, my job here is where I should place these 2 point loads. The distance between them cannot be altered, but where I should place in a span of 6 meter, where I should place them to get maximum bending moment. For that one, the explanation is given here. You can see this. To get maximum horizontal bending moment, the loads must be placed in the same way as placed for the maximum bending moment by proportioning. How it is, you just observe here. How it is. My job is to find out m raised to h. M raised to h. That is maximum horizontal bending moment. Bending moment due to horizontal forces. For that one, I need to place the loads at a specific location and find out the bending moment. But here it is more simplified now. It is more simplified. Now observe this. How simply it is done here. Huh? You don't have to do any calculation here. If you know this proportioning here, I'll show you that one. You look at this particular values. Try to understand these values so that you don't have to actually calculate the reaction, bending moment and all. Directly it is available now. Now 236.02 is what? Is one of the reactions in that problem. In that case, 2 reactions were there, no, 2 point loads were there. So in case of vertical, okay, I'll do like this. Observe here. This line, this green, whatever values you are seeing here, this is related to vertical bending moment. So when 2 point loads were there, each of 236.02, I got the bending moment 355.25. when 2 point loads of 8.625 are there, how much bending moment I will get? It is just simply ratio and proportion type of a problem now. So what you should understand here is when there were 2 point loads of 236.02 vertical point loads, I got a moment of 355.25. When 2 point loads are acting 8.625, how much is the bending moment? You can see this 8.625. This is one method, short method. If you want to use ILD, influence line diagram, and place them at a specific locations, the way I have solved that case, vertical bending moment case, by placing the bending moment 3/4 one midpoint and all, you can do that. You can do that, but it is take time and it is complicated for you. Any questions are there? Any questions are there here? See, now 236.0 to 355.25. What are these two numbers? Then only you'll understand 8.65 m raised to h. As I told you in this step, what I'm doing, this step number is 4. In the step number 4, I'm trying to find out maximum horizontal bending moment. Okay. Now, if you know what is there in this yellow color box, what is that? 236.02 giving me 355.25 moment. Similarly, if I place 8.625 2 point loads, how much bending moment I will get? So simply mh by 8, use this ratio like this, mh by 8.625 is equal to 355.25 by 236.02. From this, find out mh. Simplest way is this. So any questions are here? Any questions regarding these values? I already told you there are two ways of finding. See, look at this diagram now. Look at this diagram. Horizontal forces are acting. Okay. Now, our job is where I should place these two horizontal forces to get maximum horizontal bending moment. For that one, I should go back to analysis of determinate structures. I should study influence line diagrams. Then I should place these two at a specific location so that maximum horizontal bending moment I can get it. That is one way. Second is very simple. What I am telling you right now is easier than that. What it is, this simple box you see here, green yellow color box is there. See, 236.02 is nothing but 2 point loads. One of the 2 point loads. If I place this one, I am getting 355.25 maximum bending moment. If I place 8.625, how much bending moment I will get? So like this, mh by 8.625 is equal to 355.25 by 236.2. So this divided by this, 355.25 divided by 236.02 must be equal to mh divided by 8.625. Like this, you can easily find the mh value. Mh is horizontal bending moment maximum. So this is what I'm giving a simple method. Otherwise, I told you, you go back to influence line diagram and again place them and find bending moment, which is not advisable here. So next page, I'll get you the value of mh. So this is the mh is 12.98 kilonewton meter. Similarly, maximum horizontal shear force for two vertical point loads of 236.02, the maximum shear force was 334.36. If you want, I'll take you back to these particular calculations. If you are confused, see, I can show you that page where it is done. Again, observe this one. Maximum horizontal shear force I have to calculate it. I don't have to shift the loads and all. From the previous case only I can get it. So 236.02 2 point loads, if I place them one on the support, one at some other distance 3.5 meter, the maximum shear force I got was 334.36. Now if I place 2 point loads of 8.625, what will be the maximum horizontal shear force. Again, same formula, it is same ratio and proportioning. You can see. So 12.21. I got two values now. One is 12.98 maximum bending moment. One more is 12.21 maximum shear force. Because see, the gantry girder should be safe even when the moments are acting horizontally. Lateral forces are also producing moments in the lateral direction. We have to check that also. Now, trial section step 3. Actually, your this one starts now. Trial section is selected like this. You can see the profile. One channel and one I sections are selected. How I am able to select ISMC 300, ISWB 550. ISWB means I section it is. ISMC 300. Remember, steel structure is always trial and error. Steel design is always trial and error. Based on the past experience only, one has to select the sections, but some thumb rules are also there for you. Now you can see here. Now let us see this is a standard profile of a gantry girder. See this one. Trial section of gantry girder. Elastic modulus and plastic modulus must be calculated. Now step 5 is related to trying a section. Let us try one profile. Find out elastic and plastic modulus for that profile. How I have decided, observe this. L by 12. Approximate depth of I section is L by 12. That is 6000. Span is 6 meters. So 6000 by 12, 500 M. Approximate depth of channel section L by 25. So for height of see for this height of I section L by 12, okay, and for this much it is L by 25, and for this much it is approximate. In that way you have to check in the steel tables. So what I will do, this is L by 25. Okay, this color I'll change it. So red is L by 25. I'll check. This is L by 12. I'll check. Okay. So horizontal is L by this one. See, L by 12 is 500. 500. I have to search anything which is more than 500 now. 500 or that's why I have taken 550. 500 also I can try, but you can try that. I just tried with 5 instead of 500. I wanted to be on the more safer side. 6000 by 12 is giving me 500, but I have selected ISWB 550. 50 mm extra I have selected. Approximate depth of channel section is horizontal red line L by 25 240. What I have done, ISMC 300 I have selected. There is no 240. So ISMC 300 is selected. These are approximate thumb rules to start with. You may have to change the section later also. In the examination, if the section has to be revised, you don't have to proceed further. Still, you will get full marks. For that one, what you should do, I'll tell you. For example, somewhere it fails, but still you want to get full marks because you know that you can solve it. You have to prove that I know how to solve it, but I have to revise the cross sections. I have to revise this sizes of channel and eye sections. You have to write one sentence there. If you write that sentence, he has to give you full marks. Even if you don't do anything related to revised profile, because the examiner should be convinced that the student knows how to solve this problem with revised section. Again, you will get full marks for that. Normally, that is what is followed in the VTU. Now observe this. Let us try ISWB 250, ISMC 300. Weights are given. I have you just get this weight. I forgot to write it. Here, see, ISWB 550 is there. No weight. I forgot. Later I'll check it. See, this is. I have not written the weight here. Only thing is it ISWB 550, ISMC 200 are taken. Then you tabulate the values here. Tabulate the geometrical properties. See this. Section ISWB 550 area is 14,334 mm square. H is 550. Since it is ISWB 550, H has to be 550. Width is 250. I think you can follow all this. This is 250. Then TF, flange thickness is 17.6. Web thickness is 10.5, IZZ, which is important for us. Then IY, CYY is not important. What is CYY? I'll show you in the diagram. For I section, it is not required for us. ISMC 300 at 351. Again, area is given. H is there. 9. This is B is there. 13.6. 7.6 is web thickness. IZ and IY values are there. CY is we require this one. CYY, that I'll show you with respect to ISMC. I'll show you the diagram. 23.6 mm. So you need to tabulate all this first. This is your, you can see this is your step number 5. Trial section is taken. The profile remains same every time when you solve this gantry girder for your syllabus. Every time, because it becomes, see, this profile makes us easy for you to place one rail here. Rail can be easily placed. Okay. And it satisfies other requirements which you are going to learn here. What are those other requirements it is satisfying? Now let us go to the next page here. Now observe this. Here, still we are in the step number 5 only. Profile is finalized and I'm going to find out elastic modulus and plastic modulus of the section. I think I have done it once anyway, just observe. Equal area axis is already done 1 hour. Same problem I have taken, same dimensions. Now you see this. All the dimensions after noting that from that table, whatever table we created, from that table, all these are written now. 250, 550 inside to inside. Total height of the I section is 550. Channel is 300 by 90. All those thicknesses are shown here. It becomes again, it becomes a first year problem now. Find out the centroid, this, that. Now observe here. So what we should do here is first clearly write all those dimensions, thickness of flange, everything should be clearly 13.6 this side, 13.6, 10.5, okay. 17.6 is the thickness, you can see 17.6 is the thickness of the flange. All this should be clearly shown. Write this as AB, top line as AB, like this. In order to, this is a reference line. As the channel is placed over I section with its depth horizontal. Now one important observation here is how to read the values. How you are going to read the values. Now observation is like this. Channel is placed over I section with its depth horizontal. What it means here is whatever steel tables we are getting those values of IY and IZ. If you see the steel tables, they have given with respect to this position of channel section. With respect to this orientation, steel table has given you Ix, Iz values. But the orientation in this problem is like this. So with your steel table is giving the values with respect to, as I told you, with respect to this orientation of channel section. But in my problem, in this problem, orientation has become like this. So what is the change here? As the channel is placed over I section with its depth horizontal, IY of the channel section becomes IZ of the channel section. So that this statement is very important here. Don't get confused in the steel table. If you open the steel table and check channel section, the orientation is like this. In this way, it is channel section is oriented. So the values will interchange now. Values of moment of inertia will interchange because of the changed orientation. Okay. So IZ, that is IY of the channel section becomes IZ of the channel section. I'll show you this one here. Observe this. This is channel section. Channel section is here. Now this value becomes IZ, even though it is written under IY. See, this is meant for orientation of this. When the channel is kept like this is IY. If the channel is kept like this is IZ now. Whatever red is there, it is IZ. That is what it means actually, because of the orientation change. Okay. So depth of elastic neutral axis has to be calculated now. Depth of elastic neutral A1 Y1 plus A2 Y2 by A1 plus A2. So usually first year student they are asking why we should study this centroid and all. See here, even at 7th semester till you complete the engineering and all these will be there. So y bar is a1 y1 plus a2 y2 by a1 plus a2. So you substitute all this. No, it is very simple actually. Observe this one. A1 y1. You have to go back to the table and simply write these two numbers there. See this one here. Okay, I'll show you this. You are just substituting. You are not doing anything here. You are using the calculator. That's all. See this. 4564 into 23.6. Where is that one? 4564 into 23.6. Just I am putting A1 Y1. This is A1. This is 23.6 as Y1. How I'll show you the diagram also. Next is A2 Y2. A2 Y2. A2 is with respect to I section 275 plus 7.6 divided by A1 plus A2. This is what is Y bar. Observe here. Observe this diagram. I'll show you now how I'm getting, how to understand these values here, because you're just using your calculator now. This is your uh, channel. This is your I section. Now what I have done here is, what is 4564 into 23.6? Observe this. What is that? So this this dotted line is the position of centroid of channel section, which is CYY. This distance is CYY 23.6. So this is 23.6. If you see the steel table for ISMC 300, you'll come to know that. Now what is this? A1 4564 total area, because all are measured from the top line AB. This is the line AB here. Top line is AB. Okay, this is A, this is B. Now directly for channel section, total area into y bar of that section. What is A1 Y1 means what? Area into centroid of that rectangle. In the first year, what you have studied? What is A1 Y1? A1 refers to the rectangle, Y1 refers to that centroid of that rectangle. Here A1 refers to the channel section, Y1 refers to the centroid of the channel section from AB. A1 is entire channel section, Y1 is centroid of the channel section. So A1, Y1. So 4, 5, 6, 4, 23.6. You are just simply substituting area of the channel which is available in the code book, I mean steel tables. Then CYY is also there in the steel table. You are simply substituting the values. Then 14,334 area of the I section. Okay. Now let us see what is Y2. Y1 is CYY is nothing but Y1. This is, you can see in your steel table, this is nothing but CYY, that is 23.6. Now let us see how to find out the A2 Y2 of I section. So A2 is area of the entire I section 14,334. Now where is the centroid here? Where is the centroid? Centroid of the I section, where it will be? It is at the midpoint of the I section, somewhere here. This is the midpoint of Y section, but it has to be measured from the top edge of channel section. This is Y2. You can see this is Y2. This is Y1. CYY is Y1. Now you get the Y2 here. How to get Y2? Already in the steel table, you know this distance. For I section, you know this distance, which is 275. 550 by 2 is how much? That is 275. You add the thickness of the flange of the web of the channel section. Are you getting this point? What I have done here is, 14,334 is the total area of I section as given in the steel table. I am just writing it. No calculation is there. 275 is 550 by 2. Total height is 550. It is ISWB 550 means this 275 is 550 by 2, 275. But I have reached the outer edge of the I section. But I should reach the outer edge of the channel section. AB is this line. That is why I have to add the thickness of channel section. So 275 plus 7.6. Now both Y1 and Y2 are measured from the same line, same AB line. So from same AB line, Y1 is this, Y2 is this. I have substituted all those divided by total area. 4564 plus 14,334. So 220.05. So this is the centroid of this profile now. I got the centroid of the profile somewhere here. So this centroid of the profile will be 275. I have drawn this figure here. See. Okay. Is it clear this one? Any questions here? How to get this? See, it is not like the way you are calculating in first year. Again, divide them into rectangles. This that you will spend 1 hour for this calculation only. If you see, if you don't know how to do it fast, don't attempt this question in the exam. If you don't know how to calculate y bar, better to try some other example in the examination. Otherwise, it will be a waste of time here. See, this calculation you should take maximum 5 minutes. Maximum. This one, if the same problem is given to a first year student, he will not be using steel table and all. He has to divide them into rectangles and all that. He has to calculate it. He will take 20 minutes. That is valid. For that fellow, it is valid. For you people, you have to use steel table. All values are available. Only here and there, y1 and y2, you should know what are those. Once you know what are y1 and y2, it is simply 1 minute or 3 minute work. So gross MI of a built-up section. Now observe here, IZ gross. Now if you look at the steel table, observe this. In steel table, with reference to this type of profile only, IZ is given. With reference to this profile, IZ is given. That is why I told you, in this case, I have to use these two. One is this profile, one more is this profile I have to say, because it is tilted. So see this IZ gross, IZ of the beam section, IZ of the channel section. So I have to just refer the steel table and add these two numbers. Let us see that one. Okay. Now you can see this diagram. It gives you the clear picture now. Now observe here. This centroid line I'll show you with respect to whatever values I have calculated just now. I have explained. Just observe this. Now this line is what I have calculated just now. This line 275 plus 7.6. That is a centroid of the I section. It is actually I section from the top line AB. This is the top line AB is here. Okay. Just try to understand the diagram first. You worry about other things later on. Look at the diagram, try to understand what is there. Y max is 337.55. Okay. Now you look at this particular, this one here, 282.6. Center of the entire section, 282.6. Okay. Is it clear this one? Okay, 1 second. You just observe this. Just observe this diagram. Okay. Now you look at this one here. I'll show you some number here. Then I'll take you back. See this one. Y bar is 220.05 from the top reference line AB. That is Y bar. Then look at this 220.05. Same number is there. Okay. Then 282.6. What is this? I'll tell you now. What is this? 282.6. There are two axis lines here. Two horizontal axis lines are there. So this is, after seeing this diagram, after observing Y max is 337.55. Now observe this one here. What is 337.55? It is total height of the profile minus Y bar. You can see this line Y max. See, because I calculated Y bar from the top edge, in total depth I subtracted 220.05. I got Y max. Because why I'm writing Y max? Because this value is more than this. 337.55 is more than this. So out of these two, whichever is more, I should have considered. So I got these two numbers. If you add Y bar plus Y max, it is the total depth of the profile. Total depth of the gantry girder, including the thickness of channel as well as everything. Total depth it is. So 220 plus 337.55. Okay. Presently, I don't know what is 282.6. I'll tell you that one. It comes in the later calculations. Observe this. IZ gross, IZ beam plus IZ channel. How to find out this one? Because I need, see, I need a IZ value. You will come to know why it is required. IZ gross means total moment of inertia of the profile I need about Z axis. Okay, Z axis. Now, what is Z axis? I will show you. In steel structures, what is Z axis? I'll draw this figure somewhere here now. What is Z axis? I think you know this one, but you will then see this. Okay. Now, how the steel table defines this axis here? This is one line. This is one more line, and along this length, one more line. In strength of materials or in first year, this line, red line was red line. Let us say AB was Z axis. I mean X axis. But in steel structures, this line is Z axis. This is X axis, blue color. This is X axis. Along the length, whatever is there, that is X axis. This is Y axis. Y axis remains same, whether it is a strength of material or steel structures. Now Z axis means whatever we studied X axis, no, that is Z axis in steel tables. So it means Z axis is nothing but X axis of whatever we have studied in strength of material. So like this, you have to add. How I got this one, you observe this. I'll complete one more step and I'll stop it because too much of information I'm giving. So only I'll complete this one here. IZ gross I will explain. See, this is all previous knowledge only. Nothing new I'm telling here. All previous strength of material only we are extending. That's all. So IZ beam you observe here. My job is to find out the moment of inertia of about Z axis of the entire profile. Okay, how it is done. Now 749.06 into 10 raised to 6 plus some other value into this. That is Ig plus AH square, parallel axis theorem. Ig plus AH square. Now let us see. First of all, you try to understand. I am trying to find out moment of inertia about X axis only as far as strength of material is concerned. Okay, Ix only it is from the nomenclature of strength of material. Now let us see here. Iz of entire profile. I'll draw this figure again. See this one. I'll draw this figure again. You can see this. Simply what you should understand, how to find the moment of inertia of this section, which has channel and eye sections. How to do it using steel tables. It will be very fast. So 749.06 plus this. Now observe this. I'll go back to that table and see this. These two values, I'll go back to the table where those are. ISWB 749.06 into 10 raised to 6. Okay, what is this? IZ of I section, which is normally placed as per the steel table only, it is oriented. So no question of changing anything here. That is, it is like this only. So IZ is 749.06 into 10 raised to 6. See this. 749.06 into 10 raised to 6. That is directly IZ of the entire profile is IZ of I section plus IZ of channel section about the centroid of the entire profile. Now I'll show one more line here. One more line. I'll show the centroid of the entire profile is somewhere here. Okay. Centroid of okay. Now this is CYY. First line is 1, 2 is first axis, 3, 4 is second axis. Now this distance is 23.6. CYY is 23.6. What is that one? Centroid of the channel section. Now you look at this formula here. That is IZ of the section is this one. That is IZ of I section. It is IZ of beam. Observe here. IZ of beam. Now observe this. What is this particular value? Okay. So what I have done here is initially I have calculated IZ of I section, then IZ of channel section, then I have added them. See this. IZ of B means I section. So IG plus AH square. This is IG plus A of I section it is into this distance. 226, 282.6 minus 220.3. So here 23.6 term is coming actually in this case. Here it is. So AH square, A is area of the I section, H. Can you understand what is this H? Can you tell me what is this H? I'm telling you IG plus AH square. If anybody has understood, you can tell me what is H, how I got it. For example, this one, you look at this, how I got this one. I'm telling you it is simple parallel axis theorem, IG plus AH square. Can anybody tell me what is this? H, how I got it? If you don't know, I'll go back to first year and again I have to tell you what is what here. If you know it, you can tell. Otherwise, I'll explain that also, which was there in first year actually. Okay. Now, I will remove this diagram. For the time being, I'll remove this. Okay, this is removed. Okay. Now see this one. Only I'm trying to explain again and again IZ beam only. IZ beam is you remove the channel section and look at only beam section, I section. See, in order to understand IZ beam, you look at only this diagram. How I got this one. So this is 749.06 into 10 raised to 6 is the IZ of I section, AH square. Are you getting this point? A into H. A is area of this I section. H is distance between two horizontal lines. Which are those two horizontal lines? I'll show you. This H square I'll explain. I'll try to make it clear. H square. Now I'll draw these two lines. One is here.
ಆರಾಮನ್ಲಿ ಹಾ ಆರಾಮ ಮನ್ಯಾಗೆಲ್ಲ ಆರಾಮದಾರ
ಎಲ್ಲರೂ ಆರಾಮದಾರು
ನಮ್ಮಲ್ಲಿ ಆರಾಮದಾರ ಯಾವಾಗ ಹೋಗಿದ್ ಬೆಳಗಾಂಕ
ask her, somebody ask her to mute it. So this one, see this is two lines, 220.05 minus 23.6. What are these two lines?
ಅಲ್ಲಕ್ಕೆ ಯಾರೋ ಶಬ್ಬು ಬಂದ ಅಂತ ಅವ್ರ ತಂಗಿ ಅನ್ನತಿದ್ದಲ್ಲ
Okay, are you getting this point? What I have done here, this is H. Now observe here how I use parallel axis theorem is Ij. I'm just stuck in Iz for the last 10 minutes. I'm stuck in that. Try to understand. Iz, see this. I'm trying to explain this one. It is all there in first year, but again 749.06 into 10 raised to 6 Iz plus AH square. A is area of the entire I section. What is H? I was asking. This is H. This is H. Now you tell me what is this. I'm telling you this is H. So this H is, that is 282.6 minus 220.05 is H, small h, as per your strength of material formula. This H is the distance between two parallel lines. Which are those two parallel lines? One line is centroid of the entire profile including channel section. One more line is centroid of only I section. This is what is 282.6 minus 220.05. So I'll repeat this one here. Observe. Ig is there in the table, steel table. Then area is there in the steel table, area of I section. Everything Iz, everything is related to Z section. I mean I section only here. This line is related to only I section. Now area is there in the steel table. These two values we have calculated in the previous steps. 282.6 and 220.05 are calculated. What are these two values? These two values I have shown in terms of two horizontal lines here. This is one line is related to centroid of the I section. One more line is related to centroid of the entire profile including the channel section. So these are the two lines. One line is, as I told you, centered of the whole section including channel. One is centered of only I section. So these two are the values here. 282.6. This is the position of this one minus 220.05. These are the difference. Now H is this distance. That is H. So in this way you calculate Iz of the people. Any questions here? Now Iz channel. I have to add these two gross. After this, I am going to stop it. Now see this. Now I section is completed. Now see this. I want the moment of inertia of this. Okay. Observe. Channel section 310.8 into 10 raised to 4. Okay. What is this? What is this one? 310.8 into 10 raised to 4 is, I'll take you to the table again. 310.8 into 10 raised to 4. Remember, say you should use IY here. Don't use this value because these two are reversed now. Because of the orientation is like this. Orientation is like this. Because of this, you should use IY even though I'm calculating IZ because of this type of orientation. We have to interchange those two numbers. Now that value is added now. So 310.8 into 10 raised to 4. So what is important here is this value is IY in the steel table. IY of the channel, it is 310.8 into 10 raised to 4 plus area of the channel and H square, IG plus AH square, IG AH square. So A is area of the channel, H is again, see this, what is this H? I'll show you, observe this. What is H? Again, I will define, observe this. In this, with reference to channel, I am going to define this H. So somewhere here, I'll draw this line. Somewhere here, I'll draw this line here. This is 220.5. Entire centroid of the entire section is 220.5. Centroid of this channel is here. Channel is here 23.6. So I want this distance as H square. So channel section is 310.8 into 10 raised to 4 IG. A is 4564. H is this distance between two parallel lines. One line is, see, one line is with reference to the centroid of the entire section, which is 220.05 from the top. So this line, whatever I have shown here, I'll call it as AB. What is this AB? AB line is centroid of the entire section. CD is centroid of the channel section. Difference between these two is H. So it is 220.05 minus 23.6. I'll get this H value. So in this way, we have to calculate channel section and I section, IZ values. Just add them. Okay. This is what is 9.84 into 10 raised to 8. So you have to go back and study this one, because as I told you, this problem, as I told you, it is all about geometrical properties initially. Only I have selected one profile and I am trying to check the strength of this profile. Because already maximum bending moment is calculated. I am checking whether the moment of resistance of this profile is sufficient or not. Because in the previous steps, maximum bending moment was calculated. So for this profile, I have to calculate the maximum, that is moment of resistance. That value should be more than maximum bending. In order to find out the moment of resistance, I need IZ values. Once I get IZ, because as you know, it is moment of resistance is equal to sigma into Z. Moment of resistance is stress into section modulus. You have studied in strength of materials. What is that? Moment of resistance is equal to stress into section modulus. So still I have not calculated section modulus. I need IZ to find out section modulus, because section modulus Z is I by Y. I have reached only I now here. Still I'm in I here. Now and IY of the compression flange. I think I'm going to stop because it is too many things I am telling you on one day. But anyway, this is, I'll stop after this. IY of compression flange. It means entire channel section is in the compression zone and the flange of the I section is in the compression zone. This part we are going to neglect, even if it may be there. This vertical part of the I section may be there in the compression zone only. That we are not going to count. That we are not going to consider. So IY is equal to IZ of channel. See this. You look at this diagram. Some concentration is required now. You look at this diagram. So I am trying to find out IY of the compression flange. It means about this line. About this line. Now you can go back and like imagine like first year only. There is one section like this. and one rectangle is there. It means effectively there are three rectangles of channel and one rectangle of I section. If you want to go back to first year, in that way I'm telling, you can split it into three rectangles for a channel section and one rectangle for I section. This white part, whatever is there, no, that is not considered. It can be neglected. So for these two, that is channel and rectangle, I want moment of inertia about this vertical line now, YY. That is what is there here. So IY is equal to IZ of channel section because the orientation is like this, plus rectangle TF BDQ by 12. BDQ by 12. That is how I've calculated here is BDQ by 12, how it is done. For this rectangle, whatever is there, this rectangle, it is simply BDQ by or DBQ by 12. We can say DBQ because it is Y axis line. D into BQ by 12. So D is thickness of the this one flange. BF is this width of the rectangle. So what 17.6 into 250. This is 250 here. This one is 250. Thickness of this is 17.6. So first find out moment of inertia of this rectangle red color about y axis dbq by 12. It is here. Then moment of inertia of the channel section about y axis. Since it is tilted, I will refer steel table for this and I write iz of channel section. See this. Why iz? Because it is tilted like this. It is not in this fashion. So directly I'm getting this value in the steel table. This I have to calculate it. That is BDQ by DBQ by 12. So in this way, I'm able to find IY of the compression flange. Why this is required? You will come to know in the next step. Why I need only this part, only this much IY, why it is required. So you remember this white, whatever portion is there, no, that is a web portion of the I section is not considered. It may be in compression zone only, but it is not considered. So finally, 6362.2 into 10 raised to 4. That is what I am doing here. This is directly I am using the steel tables. See, don't be under the impression that it will take a lot of time in the exam because all these values are available in the steel tables. Here and there you are calculating using calculator. Otherwise, most of these values are there in the steel table only. So finally, IY of the compression flange is